Welcome to the 9th lecture for Chemistry 418, Nuclear Chemistry. This lecture is on nuclear reaction and it's in 2 parts. The readings for nuclear reactions are listed here: Modern Nuclear Chemistry, Chapter 10, and Nuclear and Radiochemistry, Chapter 4. The first part of the lecture on nuclear reactions will cover nuclear notations. We've already described nuclear notations. We've used them in the course. We will formally go over them in this chapter. We'll also discuss the energetics of nuclear reactions within part 1. And we'll talk about some reaction types and mechanisms. We'll talk about the need to overcome barriers in reactions. Charged particles need to overcome the Coulomb barrier. Neutrons do not need to overcome the Coulomb barrier. Big difference in the way neutrons and charged particles react. We'll also talk about scattering. So not only a reaction where a target will combine with a projectile coming in, but also reactions where the projectile actually, the Coulomb repulsion between the projectile and the target forces the projectile to scatter away. We've discussed this and explored how one can measure the size of nuclei through scattering reactions. Then we'll end part 1 where we'll talk about nuclear reaction cross-sections. We've introduced the term cross-sections. We've used their values in equations to calculate yields from nuclear reactions. We've discussed the size of cross-sections, that one barn is close to the physical cross-section occupied by a nucleus. But if you remember, looking at some of the cross-sections, there are multiple barns. Some are even thousands of barns. We'll discuss how is that possible where you can have this term for the cross-section which would represent a size of a nucleus that's 1,000 times larger than it actually occupies. And the real answer is that what we're really talking about wave function overlaps, and anything on that level, we don't really utilize Newtonian physics, but rather quantum mechanics. Within part 2 of the lecture on nuclear reactions, we'll talk about some observables with reactions. We'll discuss scattering and direct reactions with a little bit more detail. Then we'll talk about compound nuclear reactions, photonuclear reactions, where a photon is one of the particles. And then we'll end the lecture talking about nucleosynthesis, where elements are made in stellar processes, so how elements are made in stars. Overall, this lecture will cover what's described and shown here in this figure. We'll have a projectile hitting some target. A reaction occurs, very short time period. We may have a dinuclear system. The nucleons can start interacting. This reaction product can then reseparate before complete fusion. It could swap some nucleons. Some of the projectile may scatter off some nucleons from the target. And as is shown here, we can get a number of different products from this reaction. There's also a possibility that this dinuclear system fuses to form this compound nucleus, where we have one nucleus that is a component of both the target and the projectile. This compound nucleus can de-excite by breaking up, by fissioning, by having a segment of it come off, or the compound nucleus can actually remain together and de-excite through emission of photons. So we can go everywhere from this initial reaction to make all sorts of products, and each one of these products can be described with a cross-section. We'll describe within this lecture how cross-sections can be measured. We already know how to utilize them, and we'll explore different ranges of cross-sections and cross-sections for different types of reactions. We'll start off talking about nuclear reactions, just defining them. They're just a reaction with a range of particles. A nuclear reaction can occur with a nucleus, a subatomic particle, or a photon to produce other nuclei. So fundamentally, we're looking at a change of a target into a new daughter or a new reactant. These reactions are in short time frames, picoseconds. The first nuclear reaction, as we discussed early in the class, is from Rutherford. What reaction was this? Well, that reaction is listed here. where an alpha particle is impinging on some nitrogen and forms some oxygen and a proton. Another way of writing this reaction, we've discussed in class, but we'll formalize it, is shown here, where we have the target as the first term, the projectile, here it's helium, we'd write that as an alpha particle. Out comes a proton, which is separated by a comma in parentheses, and then the product, which is oxygen 17 in this point. Now, with a number of reactions, with these nuclear reactions, a number of terms and particles that are going to be conserved in the reactions. For instance, the number of nucleons. Generally, the energies that we're involved with, the number of nucleons are going to be conserved. This isn't necessarily true at higher energies where you can involve creation or annihilation of nucleons. Charge, energy is conserved, energy with mass, momentum, angular momentum, and parity. You can imagine that all these terms can be used to help describe reactions and help understand reaction mechanisms. As we've already discussed, there's a Q value which describes the reaction. Q value is the energy of the reaction. If it's positive, it corresponds to energy release, negative energy absorption. And Q value, as we discussed earlier, is energy in terms per nucleus transformed. We can use some of this energetics to get an idea of the overall reactions involved in nuclear reactions. So if we take the reaction we discussed on the earlier page, we calculate the Q value for this reaction. The Q value is a little bit under, it's just around -1 MeV. Now to describe this sort of reaction, can talk about this on a per molar basis so we can compare it with a chemical reaction. We use a conversion term of 1 MeV is equal to 1.6 times 10 to the minus 13 joules. So we can describe our reaction from MeV to atom into joules per mole, and we see that this reaction winds up being on the order of 1 times 10 to the 11th joules per mole. And these reaction energies are so large that mass change is observable. It's good to remember that chemical reactions tend to be on the order of kilojoules per mole. And that's one of the reasons this is a reaction that requires energy. But for instance, fission, which gives off energy, shows why that can have such high energy densities. Let's continue evaluating these energetics in reactions and discuss the Q value. The Q value is not necessarily equal to the energy that's necessary for the reaction to occur. Oftentimes, a reaction to proceed forward will need to overcome and be greater than the Q value. And this is because products will also have kinetic energy that need to come from the reaction. The Q value, as we'll see, is a center of mass reaction, and we need to convert this to the laboratory frame. This is due to the fact that there's conservation of momentum. The particle kinetics energy must be retained as products kinetic energy. So in other words, all the energy of the system that's defined by the Q value is not necessarily available just for the reaction. Some has to go into moving the resulting products. And the amount that's retained as kinetic energy of product is based upon the projectile mass. The retained kinetic energy becomes smaller as the target increases with the equation that's listed here, where if I take the Q value and multiply it by the fraction of the mass of the projectile divided by the mass of the projectile plus the mass of the target, I'll get something called the equation for the kinetic energy that's necessary for the equation. We'll see this is going to eventually come into something called the threshold energy. Now let's look at this and think about what does this mean for a reaction where I have something where I'm making compound nucleus. Let's make this a relatively straightforward reaction. Curium plus oxygen 18 going to rutherfordium 266. What does this mean if I either accelerate oxygen into a curium target or curium into an oxygen target? Well, if I accelerate the curium into an oxygen target, I use the curium as a projectile, this value, this kinetic energy, is about equal to the Q value. So we see because it's equal to 248 divided by the sum of 248 plus 18. Now if we go the other route, which is actually done experimentally, where we accelerate oxygen into curium, we wind up with only the kinetic energy being a smaller fraction of the Q value. This is one reason why you often accelerate the light particle into the heavier target. Now we can use the equations we just discussed to correctly evaluate what energies are used for a reaction to occur in the laboratory. And what we need to do, we need to consider both a laboratory and center of mass frame. For the laboratory frame, we need to consider the conservation of momentum. So in a laboratory, here's an example of a target. A projectile hits the target. We get our product and the other product from the reaction. Both the two products are moving. The particle that impinged upon the target, we can basically stay stationary. The particle moves and we have two other bodies that are moving. So we need to consider the fact that the products are moving after the reaction. They're moving at a certain energy, a certain velocity, and at a certain angle from the initial trajectory of the projectile. Now there's an equation here where we see that the Q value can be a sum of terms related to masses and the kinetic energy. So the kinetic energy of X would be the particle here. The kinetic energy of P is our projectile. And we also have information related to the kinetic energy of the product. And this allows us to consider evaluate the reaction if we know product information such as the angle in which one of the products come out of the reaction and its energy. We can find the Q value if that angle and the kinetic energy of X are measured and particles known. So if I look at this equation up here, I see that I have certain terms where the Q value is a function of different kinetic energies. This equation here relates these kinetic energies to values that can be measured, masses, and something that's known from the experiment, such as the initial kinetic energy of the particle. So if one can measure the angle and the particle kinetic energy, one can find the Q value of the reaction. Now for center of mass, where we often do equations, the total particle angular momentum is 0. In this case, it's as if the products and the reactants are hitting each other, and we get a center of mass frame that looks as shown here. We can talk about the kinetic energy from the center of mass and evaluate the two equations where we relate the kinetic energy of the center of mass and the kinetic energy of the lab, and it just winds up being equal to the kinetic energy of the center of mass is equal to the lab times a ratio of the mass of the particle and the sum of the mass of the particle and the mass of the target. The equations we just evaluated can be used to determine a threshold energy for a reaction, so the minimum energy that's necessary for the reaction to occur. We have this relationship where the Q value plus the kinetic energy of the lab minus the kinetic energy of the center of mass has to be greater than or equal to 0. We can solve for terms related to the relationship between the center of mass, the kinetic energy, and the laboratory kinetic energy. So we substitute the kinetic energy of the center of mass for the laboratory kinetic energy times the ratio of the mass of the particle divided by the sum of the particle and target. We come up with the rearranged equation, which is listed here. We've put the Q value onto the other side of the equation.
We take the kinetic energy of the lab term out. Now we can rearrange this equation and solve for what the kinetic energy of the laboratory must be greater than. We get to this equation here. We rearrange. We substitute the mass for A, which is a good, reasonable substitution. And we come up with this very simplified equation where this threshold energy, this minimum energy for the reaction, has to be equal to the opposite of the Q value times the mass of the projectile plus mass of the target divided by the target mass. So you can use this to evaluate should we use a heavier target or a heavier projectile. And as we discussed earlier, by inspection we could see that we'd prefer to use a heavier target if possible. Using what we've just discussed, we can evaluate the threshold energy for this Rutherford reaction. Our reactions listed here. Let's take our terms, put it into our threshold energy. Our Q values listed here, projectile, target. This equation is transformed. The terms are listed here, and we get 1.5 MeV for the threshold energy. Now this is just the minimum energy for the reaction to occur, and it doesn't account for the Coulomb barrier. The Coulomb barrier is the charge interaction that we need to overcome to get the two particles right next to each other. The Coulomb barrier comes from the fact that I've got to take these charged particles and contact them. So the equation for the Coulomb barrier is listed here is a function of the charges, and this is our term describing the charges, divided by the radii. If we use this equation for the radii, where nuclear radii can be approximated with a constant times a to the 1/3, we can substitute this equation and show a Coulomb barrier, which is just a relationship of a constant, the z of the projectile, z of target, the a of the projectile, the a of the target. This term for since this term for the Coulomb barrier is based upon R naught, you may see some variations in this equation. This equation that's listed here that we're substituting and going to put into our terms is used for an R naught of 1.5 femtometers. So we can take this term, put in our terms, the terms coming from our Rutherford reaction, where we get the Z's and the A's, and we see that the Coulomb barrier is equal to 3.36 MeV. This is a center of mass equation, and we need to convert this into a laboratory frame, so we multiply the terms by the ratio of the target projectile divided by the target, and we see that what's needed in the laboratory is a alpha particle with an energy of about 4.3 MeV needed for this reaction to occur, which is what Rutherford was able to see. The values for cross-sections as we look in the chart of the nuclides can be well under a barn to many thousands of times a barn. So that really raises the question, how can these values be so large, particularly if we discuss a reaction in terms of a particle impinging upon something the size of the nucleus? Well, this pi r squared cross-section, which is fundamentally close to a barn, is approximated at high energy. However, the wave nature of particles has an upper limit of reaction that it can include the Broglie wavelength. So fundamentally, this equation, pi r squared, can go to pi r plus the Broglie wavelength squared. So the cross-sections can be larger due to incoming particle wavelength. And if you think about that, the cross-section values change with the function of energy of the particle. The target itself doesn't influence the variation in cross-section. There are some terms that we need to think about to discuss this further. The main one is an impact parameter. Here's a picture of an impact parameter, B, which is fundamentally the target closest approach to the nucleus. So it's a term that we can evaluate and try to utilize to determine something about a reaction probability. we can evaluate the cross-section through using the impact parameter and the system angular momentum along with the de Broglie wavelength, where this impact parameter can now be replaced by this quantum term, the angular momentum, and the de Broglie wavelength, the wavelength of the particle. Now we can look at this, and the impact parameter can have any value between 0 and r. So the equation, the possible ranges are listed here, and where the orbital angular momentum is equal to 0 to b, where we can now sum all these terms from 0 to the maximum value of the orbital angular momentum. And we can see that the cross-section is now going to be based upon a summation of the system angular momentum cross-sections related to the impact parameter. And it's for this reason that nuclear reaction cross-sections can be much larger than the nuclear geometric cross-section, so the physical space. And this is really manifest by slow neutron reactions. Some of the details that we just discussed are listed here, where the cross-section for any angular momentum can be derived from this equation. And we can see that if we take this equation and expand it, this is for a given angular momentum, expand it for all the angular momentums, we can see that this equation winds up expanding into this term. And fundamentally, the cross-section now expands to the different angular momentums. And this represents a summing term, which is the reason that the cross-section can be much larger than the geometric mean. Now, one of the things that are somewhat limited in this, this is a good general trend for slow neutrons. However, there are some physical parameters in cross-sections that prevent values from, or that force values to change as a function of energy. So here's what we just discussed for the thermal neutrons. Their low energy resonances are large. These cross-sections are large. As the energies increase, the de Broglie wavelength changes. It becomes much smaller, and the cross-sections start coming towards, say, physical sizes. Now, charged particles, which are shown here, they have to overcome the Coulomb barrier, as we discussed with the threshold energies. So there are certain energies which we will not have any nuclear reactions. So those cross-sections start low, they increase, and they eventually start going towards geometric cross-sections. Measurements can be performed to evaluate this change of cross-section with energy. Those are called excitation functions. And as we see here, there's some data for this is experimental. These are calculations. The experimental is for proton-induced reaction on copper-63. We see that if we hit copper-63, everything here has a proton. The products that come out could be a neutron, proton-neutron, proton-2-neutron, or 2 neutrons. So if we perform a reaction, we provide information about the products, we can get cross-sectional data by looking at the change of the product concentration as a function of energy. We can actually perform these experiments simultaneously if we have number of different targets in a system. So if I put in a number of different copper foils and I expose this to a single beam, each time that beam passes through one copper foil, it'll decrease in energy. So I can evaluate different energies and obtain data from multiple reactions at a given time. Now, if I were to go to the chart of the nuclides and look what would happen if I added a proton to copper 63 and emitted a neutron, or proton and a neutron, or proton, 2 neutrons, or 2 neutrons, I would see that I would have a range of different products. We can evaluate these products through their radioactive decay, measure their rates of formation, and if we measure their rates of formation, or the total amount that was formed, we can get the cross-sections. So we see that we can provide that for a reaction with many different outcomes or different particles outcomes, so for instance a proton or a neutron. And here's an example of a reaction where we just get 2, 3, 4, or 5 neutrons out. Now this is experimental, this is calculated, and the reason we'd be interested in these calculations is that if we wanted to perform this experiment with calcium and berkelium, we'd want to get an idea of what energy we should perform the experiment at. And if we see we have the center of mass energy on the order of 210 will give us the 3N reaction maximum, 215 will give us the 4N reaction maximum, and we'll also get an idea of the cross-section here listed in picobarns, so you can get an idea of the rate of formation.
A final comment we'll make on reactions has to do with the barriers from the charged particles. There's Coulomb repulsion between the charged particles and the bombarding nucleus, and this is a reason that cross-sections have a threshold. One of the reasons they have a threshold energy, for instance an alpha particle reaction with antimony or proton with zirconium, they have to overcome the Coulomb barrier so that a minimum energy is needed for a reaction to occur, and this occurrence is obviously reflected in the cross-section measurement. Now it is possible for a particle to tunnel through the nucleus and have a reaction, so it doesn't necessarily have to overcome the Coulomb barrier, but the probability of tunneling drops rapidly as the energy of the particle decreases. So we're at the lower energy end, so we have a relatively low tunneling probability. However, this has been used for some reactions to drive a reaction below the Coulomb barrier and just rely upon the tunneling effect. Now these Coulomb barriers are also going to have an impact on the charged particles entering and leaving the nucleus. The charged particles that are emitted from the nucleus can experience an acceleration due to this Coulomb repulsion, and we've discussed this with when we discussed beta decay, and we talked about positron emission from the nucleus can be energetically favored due to this repulsion, and we gave an example with the copper 64 nucleus. Now, based upon what we've discussed on reactions, there's a few things that are demonstrated here. One is that we have this minimum threshold energy due to the Coulomb repulsion, and then there's also a maximum cross-section that is defined by a given energy in which the highest probability of the reaction occurred. So in the case of this reaction here, the antimony with an alpha particle 3N out and the iodine 124, an energy of around 35 MeV is a maximum, whereas this reaction where we have a proton on natural zirconium making niobium 96, the maximum energy for this reaction at the highest cross-section, which is only around, let's say, between 15 and 20 millibarns, is at 8 MeV. This concludes part 1 of lecture 9 on nuclear reactions. Part 2 covers the information shown here: reaction observables, scattering, direct reactions, compound nuclear reactions, photonuclear reactions, and nucleosynthesis. Please continue on to that lecture when you've completed this one.